Hey everyone, welcome back. Let us take some more examples and analyze the time complexity. Our first example for this video is now let's see how we can analyze the time complexity of this for loop. For this case, I'll just consider a table and we'll try to dry run for each iteration. We have variable I and P. That's it. In this case, let's consider n as 5. I starts from 0, 0 less than or equal to 5, which is true. Now update statement gets executed, meaning the statement inside for loop gets executed. In this case, P gets updated to 0 plus 0, which is 0. Now update statement of for loop executed. I gets incremented to 1. 1 is less than or equal to 5, which is true. Now the statement inside for loop gets executed. In this case, what we are doing is we are taking the current P and adding I to it. Current P plus what is I? 1. Now I gets incremented to 2. 2 is less than or equal to 5. Take current P, which is 0 plus 1, and add I to it. I gets incremented to 3. 3 is less than or equal to 5, which is true. Take current P and add I to it. I gets incremented to 4. 4 is less than or equal to 5, which is true. Take current P, 0 plus 1 plus 2 plus 3, and add I to it. Just draw an arrow here. After fourth iteration, I gets incremented to 5. 5 is less than or equal to 5, which is true. Take current P my bad and add I to current P. Now I get incremented to 6. Is 6 less than or equal to n, which is 5? No. This condition fails. For loop breaks. In this dry run, we know n, so we are able to find the number of time it gets executed. But what if n is unknown? We will not be knowing when the for loop stops, right? In that case, we can just consider that unknown number as k and I gets incremented till k, right? What we can do is we can have k here and we are considering n as k. So k will be always less than or equal to n. So the statement inside for loop gets executed. We'll take the previous p and add k to it. 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus and some iteration. At the end, we will be adding k. This k is unknown to us for now. We need to find the k so that we can find the number of times that for loop statement gets executed, meaning the statement inside for loop gets executed. That's our time complexity of above example, right? Now, out of this thing, can't you identify the formula? We have seen in our previous video, right? This is nothing but sum of n natural numbers. Hence, P equals 0 plus 1 plus 2 plus 3 plus 4 plus until k, and this can be written as P equals k into k plus 1 by 2. This formula is nothing but sum of n natural numbers. Our goal is to find this k, right? Now let's check when our for loop is stopping. Our for loop runs until p is less than or equal to n, and it stops when p is greater than n. This will give the lead to find our k. For loop stops when p is greater than n. We know p, which is nothing but k into k plus 1 by 2, which is greater than n. From here on, it is just basic mathematics to find the value of k. To remove this denominator, we will multiply both the side by 2. Multiply both sides by 2 to remove denominator. 2 into k plus 1 by 2 greater than 2 into n. This two gets cancelled. We'll end up with k into k plus 1 is greater than 2n. Now we can do multiplication here. K square plus k is greater than 2n. Finally, we have this equation. Now, in the time complexity, we will always focus on dominant term, which is the dominating term here, k square, right? Let me just give example for this. Why we will be considering k square going forward. Let's consider k as 1000. If k is 1000, what is the value of k square? Which is nothing but 10 lakhs. And what is the value of k? 1000. Is k square is same as k? K is very small compared to k square. And this is kind of constant time. So that's the reason in time complexity we will always consider the dominating term. So approximately we can ignore the smaller value, that is plus k. After ignoring the smaller values, we will get k square greater than 2n. Now to get rid of this exponent, we'll take square root on both the side. Take square root on both sides. Root of k square greater than root of 2n. And this gets cancelled. K is greater than root 2n. Can we split this? K is greater than root 2 into root n. In terms of time complexity, this is very constant, so we can ignore root 2. We'll end up with k is greater than root n. We got to know k is root n, and our for loop runs until p is equal to root n. Whatever the number, it runs until it is root n. Therefore, the time complexity of above for loop is big O of root n. I hope this thing is clear. Let us move on to our next example. Our second example for this video is for I starts from 1 and goes till n but gets incremented with multiple of 2 for every iteration. And we will be having some statements inside for loop and we'll end the for loop. The difference here is the initialization part and condition part is almost same, almost similar to our previous for loop examples. But the catch here is the update statement is getting updated by multiple of 2. Let me just take down the table and explain it. Update statement. For this dry run, let us consider n as 10. I loop starts from 1. We are not starting from 0 for this example. I, and after executing the statements, we'll keep track of that as well. Let me just add one more column here. Times executed. When I is 1, this statement gets executed one time, and after executing the statements, update statement will be executed. We are updating the value of I by I into 2. I is 1 into 2 is nothing but 2. Now in the second iteration I is 2, 2 is less than 10. The statements inside for loop gets executed one time. After statements are executed, update statement will run, which is we are taking the value of I, in this case 2, and multiply it by 2, which is 4. Now I is 4, 4 is less than 10. So statements inside for loop gets executed one time. Now update statement of for loop will run. Take I and multiply it by 2, 8. Now I is 8, 8 is less than 10. Statements gets executed one time. Now update statement of for loop will run. Take I, multiply it by 2, which is 16. Now I is 16. 16 is not less than 10. So for loop breaks here, and that's the end of for loop execution. In this dry run, we were knowing the value of n, right? That's the reason we were able to run until it is less than n. But what if we don't know n? Until when this for loop will run if n is unknown? That depends on update statement, right? For that, what we can do is to find out the term, let's see how update statement is getting updated. All these values are multiple of 2. Can't we just simplify these things as 2 to the power natural numbers? In this case, which is 2 to the power 1, and this is 2 to the power 2, this is 2 to the power 3, and this will be 2 to the power 4. I hope you are able to understand this generalization. Our for loop will run until 2 to the power something. Isn't this correct? Can't we consider this something as k? Yes, we can consider that something as k, and we'll find this k to find how many times our for loop gets executed, which will be our time complexity. We know that loop runs until I equals 2 to the power k, and this k is unknown for now. We need to find out that. As we have seen in our previous example, to find out k, we'll check when our for loop will stop. When is our for loop stopping? Our for loop stops when I is greater than n. It runs until it is less than n, greater than or equal to n. We'll take that as a lead to find k. Our loop stops when I is greater than or equal to n. We know I, which is nothing but 2k, 2 to the power k. I is greater than or equal to n. We'll substitute I, 2 to the power k is greater than or equal to n. We need to find this k. Right now it is trapped in exponent. To bring this down, we will apply log 2 on both the sides. Apply log 2 on both sides to bring the exponent down. After applying log 2 on both the sides, our expression will look like this. And these things are just basic mathematics. You should be knowing all those things. Now using our log general rule, which is nothing but log general rule, which is nothing but log b into b to the power x equals x. Because log b into something asks what power of b gives this something. If the something is b to the power x, then answer is clearly the value of x. As per this rule, our expression will now become, I'll just repeat the same expression. We can apply log general rule for this term. After applying the rule, this term becomes just k, which is greater than log base 2n. Finally, we got to know what is k. Our for loop runs until I is greater than or equal to log base 2n. Therefore, the time complexity of our for loop is nothing but big O of log n. We'll ignore the constant. So we'll just generalize this to log n. In this example, we can observe that if you have a loop where the counter or the update variables is not incrementing, but it's getting multiplied by some number like 2 or 3, then it will get always log time. Majority of the times log n gives decimal values. We should always consider the ceiling value of log n for time complexity. I hope this example is clear. Let us consider one more example which gives the same log n time function, meaning time complexity. Third example for this video is for I starts from n, goes till 1 and gets decremented by 2. Some statements. And we'll end the for loop. Let us dry run this. We'll consider value of I and update statement of for loop. And the statements inside for loop will just keep track of the times executed. For this dry run, let us consider n as 10 and I is starting from n. In this case it is 10. 10 is greater than or equal to 1, which is true. The statements inside for loop gets executed one time and the for loop update statement will run now, which will update the value of I by dividing by 2. I is 10, 10 by 2, which is nothing but 5. Now I got decremented to 5. 5 is greater than or equal to 1. Statements inside for loop gets executed. Now for loop update statement will be triggered, which will take the value of I divided by 2, which becomes 2.5. Integer value will store this as 2, but for our understanding purpose we'll consider 2.5. Now I is 2.5. 2.5 is greater than or equal to 1. Statements gets executed one time, and the update statement of for loop gets triggered. 2.5 by 2, which is nothing but 1.25, and this will be stored as 1 in integer, but for understanding purpose we'll consider 1.25. Now I value gets decremented to 1.25. 1.25 is greater than 1, so statements gets executed one time. Now for loop update statement will run, which divides value of I by 2, which will be 0.75, and this will be stored as 0 in integer. I gets decremented to 0.75. Now our condition is checked. Is 0.5 greater than 1? No, it is less than 1. So our for loop breaks here. Our for loop execution is ending here since we know the value of n. But what if we don't know the value of n? Until when our for loop executed? That thing we need to find to get our time complexity, right? To know that, let us see how our update statement is getting updated. We'll see if we can get the pattern out of this. Getting decremented to 5, 2.5, 1.25, 0.75. Okay. Can't we write this as n by 2 and 2.5 as n by 4, 1.25 as n by 6, sorry, n by 8, and 0.75 as n by 16. Can't we write this way? Yes, all values are proper. Now, if you observe, all the denominators are multiple of 2. Can't we still more generalize this to n by 2 to the power 1? This as n by 2 to the power 2, n by 8 as n by 2 to the power 3, and n by 16 as n by 2 to the power 4. Yes, all values holds good. After finding out the formula, until when our for loop gets executed? Our for loop gets executed until n by 2 to the power something. Isn't this correct? Yes. We can consider this something as k, so that we can find the value of k to find the time complexity. For each iteration, I is getting updated to n by 2 to the power k. Therefore, I equals n by 2 to the power k. To find this k, we need to find when our for loop is stopping. Our for loop stops when I is less than 1. This gives a lead to finding k. For loop stops when I is less than 1. We know the value of I, which is nothing but n by 2 to the power k. We'll substitute the value of I here, n by 2 to the power k is less than 1, and we can take 2 to the power k this side, which becomes n less than 2 to the power k. To bring this exponent down, as we have seen in our previous example, we'll apply log 2 on both sides, log 2 n equals log 2 into 2 to the power k. As per log general rule, we can just write this as k. Our expression becomes log n equals k. I've just written less than as equals. This might confuse you. I'll just revert that. We got to know the value of k now, which is nothing but log 2n. This can be written as k is greater than log 2n. Therefore, the time complexity of our for loop is nothing but big O of log n. After ignoring the constant 2, the time complexity becomes big O of log n. I hope all the three examples of this video are clear. That's it for this video. In the next coming video, we'll be seeing some more 2 or 3 for loop examples. Thank you all for watching. See you in the next one.